developed many different open source frameworks in the ecosystem, and I'll talk about some of them and share how to use them, and everyone can just go and use them. So with that, let me first, I'm sharing a link to a blog that or one of our lead data scientists wrote about concept drift. So a lot of the things I'm going to cover, if you want more details, they're covered in that blog. The different things that we're going to talk about today is first introduce what is concept drift and sort of how is it part of MLOps, or what is MLOps. We're going to talk about methodologies for concept drift detection and how to remediate that, covering some of the theory. After covering all the theory, we'll go over how to essentially build machine learning pipelines that incorporate model monitoring and drift analysis. We're also going to show feature store, part of the MRN feature store, and how it works, because feature store may be an essential piece in model monitoring, and we'll explain why, because all the feature information and statistical analysis, it could be stored in a feature store, which makes the model monitoring and drift analysis much simpler. And we'll also end with a live demo and Q&A session. So without further ado, let's first talk about what are the key challenges in machine learning today. There are a lot of things that people already know how to do, and there's AutoML, and building a model is not as complicated as it used to be a few years ago. But the real pain that people have today is how to operationalize machine learning. And there are several challenges that lead to that fact. There's known tweets that say, we built a model in the lab and it took us almost a year to productize that into like a real business application. Building a model is not a business application. You need data analytics services, real-time APIs, monitoring, logging, security, and so on. So the key challenges that we see today with most of our users is, one is that many organizations are still siloed. The data engineers don't talk to the data scientists, that don't talk to the DevOps teams. In order to build an application, it can't just stay in the research or the math stage. It has to be built as a real application, real service, or microservices, which are ready for production. And that is a very long process. I listed just some of the things you need to do along that process, anywhere from packaging your code, making it scalable, tuning, security, logging, monitoring, CI/CD, and all of those things. And even after it's deployed, then we have explainability and other sort of post-production aspects. Another critical aspect that we see in production is, assume someone created some features, created a CSV file, which is an extraction of features of historical features. And that took probably a lot of time to produce those. Data engineers, people got permission to get the data, and so on. And that's in training. Now, in order to produce something in production, you have to have access to exactly the same set of features that now need to come from operational databases, from logs, from APIs in the internet, and so on. So we usually see a big gap between having all the features ready and prepared and in the training to having the same features accessible in production with all the analytics stack that needs to go along with them. And finally, we see a lot of issues around model accuracy. Some of them relates to the previous problem I mentioned. If the features are not available in production and you're doing surveying on data which is not the same data that you did training on, probably your model will not behave the same. After all, machine learning is a math equation. If you give it different parameters, it will deliver different results. So these are the key challenges where a new discipline called MLOps is trying to address. And again, focusing on features, because features are the things that we must monitor and we must produce in order to understand essentially what's going on our model, how it behaves, or even train that. So usually we have lots of raw data. Raw data is usually not going into a model. We have to take that raw data and start combining it with other data, start aggregating it, joining it, grouping it, transforming it, scaling it, and so on. So it's becoming data which machines can understand. Remember, machines, after all, understand zeros and ones. They don't understand cats and dogs. So we have to take that data, we have to do sort of a feature engineering pipeline. Then we turn it into more meaningful features that are usually binary or understood by machines. And those features need to go to three different applications in machine learning. One of them is the training, obvious. Second one is serving. So the same features will need to feed into a model serving entity that gets those features and produces the results. And third is the governance and the monitoring. The same features, or at least the statistical patterns of those features, need to go into a system that compares the features that are coming with the features that we trained on and with the results, or with the prediction with the result, the actual results, or predictions with the behavior of the trained results. So this is essentially the pipeline that we need to always think about, where the data and the features are the real deal. It's not really the algorithms, especially today where you have AutoML and there are many frameworks, open source or commercial tools that know how to take your data set and run many different variations and algorithms on that thing, and eventually generate the best and most accurate model based on that data. But the real problem is, how do you get the data for this training, and also how do you get the same data for production, and how do you monitor the data in production and data in training is essentially the same. So let's look into how does all this stack look like. We have three different implementations, and we'll see later on how we're going to simplify that quite significantly. But at least today, most organizations, they have three different pipelines, if you will. One is the research pipeline, where you throw all your data into a data lake, and then you're doing all sorts of batch transformations, whether it's using Hadoop or data warehouses or pandas. And then you create the training set, and that training set will then feed into your model. You're going to run a training of your model, evaluate the results of that model, test that the model works properly in all the different conditions, not just good scenarios, but maybe bad scenarios. Today, people are talking more and more about how to protect our models against sort of offensive attacks, where someone is trying to trick our model or cheat our model. Now, once you have that model, you need to build a real-time pipeline or an online pipeline, which now doesn't load data from a data lake. Data lake is just a place that we store historical data. Now we really need to tap to real data. Think about, we're analyzing fraud, so we need to connect to the actual data of our transaction database, of the customer transaction database. We need to understand potentially geolocation of a user when he's doing a transaction. That means we have to maybe get data from his mobile device and so on. So now we have online data and events that need to feed into that pipeline. Now we're doing online transformation, which are calculations that we're not going to do batch calculation like we did with the research part, where we run just very big SQL queries. You can't run SQL queries 1,000 times a second. It's going to kill the machine. So usually this is a place where you'll see things like NoSQL and stream processing and so on. And then you're doing the transformation, you're getting the online data, and you're fitting it with the model that you trained in the research and the development of the model. So that's the second pipeline, of sort of more of the deployment of your model. But now there's a third pipeline, which is growing in importance, especially because of legal reasons, because of those attacks that we've seen. We have to now see that our model is producing good results. And there are two aspects to that. We need to first monitor the model more in sort of real-time manner, and stream processing, again, see in real time that the model behaves, and monitor the number of transactions, the data, and so on. And there may be some batch transformation or batch analysis that happens later, maybe a day later, an hour later, or a week later, that looks into the behavior of our production data and try to compare the behavior of our production data with historical data. And based on that analysis, we can trigger different actions. We can retrain models, we can change add data pieces that were potentially missing, and so on. So we're mostly going to talk about the governance and the monitoring, but towards the end, I'm going to show the entire thing and how you could simplify it using MLOps. And so this is a quote. You see that data evolves over time and must be analyzed in real time. What does it mean? The best example today is COVID-19. So, a year ago, we all were used to certain patterns. People were buying the same type of things. People were traveling abroad and flying over on airplanes, were gathering in groups, and so on. And now, after COVID, those things changed. So maybe we produced a model that was learning a different behavior of people or machines a year ago, and now it doesn't behave the same because the patterns of behavior of the people is now changed. So we must be able to always detect that change and adopt our models to those changes. So we have essentially two problems. One is how do we detect the nature of the change? And second is how do we remediate? And we're going to speak about those two elements in the solution. Okay, so first, what is a concept brief? So let's assume again, I gave you this example that people that used to buy always the same type of products. If they're coming from a certain geolocation or the socio-economical a group, or maybe an age group, or or interest group, and so on, they were always buying a certain thing. So now you have the X, which is those features, and you have Y, which is the the classification or clustering, or so what they're doing that we're trying to predict. It's going to change. Their behavior is going to change. So either it's going to happen suddenly. I don't know, an airplane crash, so in that region maybe something happened. The stock market fell. Everyone is now reacting immediately different. It could be incremental. It could be seasonal, for example. In the summer, people behave in a certain way. In the winter, in a different, and so on. So we have to understand those different potential behaviors of our drift. But all of those are going to lead to essentially a situation where our model doesn't behave as we anticipated. Okay, now there are two different drifts that we can think of. One is the real concept drift, and the other one is what is referred to as the virtual drift. So let's assume that we train a model, and we create the data, and essentially we classify the data to two different classes, and everything is good. And now real concept drift is maybe when our classification is not correct anymore. Now we're getting different data points, and A and B, the way we classify them is through a different means. That's one type of concept drift. The other one is maybe we're just suddenly, our decision that maybe a guy with this age and this habits and so on likes to buy, I don't know, a beer. But suddenly we're not going to get a lot of those ages coming to visit our website. So the data changed, but the decisions, when this guy will come back, we'll still do the right classification. Our algorithm is correct, but the type of data that we're getting into our production system is not the same data that we trained on. So this is like virtual drift, and real drift is when we actually also the classification changes, the Y changes, not just the X axis. Okay? And again, think of it this way: we may get different data and still may be able to do the right classification with different data, but in some cases maybe our classification is all wrong. So that's sort of the virtual drift, and real drift is when things are really changing. Okay, when, for example, the buying behavior, as I mentioned before, is actually changing. So the same guy that is the same age group and the same habits is now making a different decision. So X is the same, but Y changed. Okay, so those are essentially the two types of concept drift. Okay, so what are the methodologies for detection and remediation? So let's look at what is essentially a machine learning system. Okay, so we get data. That data has some relevancy. If you're analyzing cats and dogs, probably the dogs are dogs and the cats are going to be cats for a while. But in every real data, there's also an element of temporality, so especially numeric data, which is true for a certain period of time. So we need some some memory window, if you will, before we go and do learning. We have to sort of filter our data according to some time domain. Then we do our learning, we generate the model, and based on that model, we can do prediction. And now we also can potentially have a feedback loop. Well, a feedback loop could be to measure the actual results. Let's assume we're anticipating that the stock market is going to go up for a certain stock, but after an hour or at the end of the day, we know if it was right or wrong. So we have labeled data just in a delay of 8-9 hours. So after 9 hours, we can essentially go and timesheet the data by 9 hours and compare it and see if our model was accurate. And based on that, we can estimate if we need to retrain, adopt, and so on. And so we need a way to detect those changes. And when we detect those changes, we can do a few things. One is to alert the system. We're not doing great predictions anymore. And the second thing is to essentially go and retrain, potentially shift. Maybe we trained on a year worth of data, but now because there's a new behavior, COVID is an example. Now we need to do training on a window that's more representative of the current situation. Okay, so then one of the changes is essentially changing the data we're looking into. Maybe adding another feature that we see is things that the system is very sensitive to a certain feature. Maybe we classify based on some age groups, and we need to classify based on the different age groups, or add some other parameters that we didn't think about. So so this is essentially how we want to look at those systems. So how do we detect virtual drift? Again, there are two things that we want to detect: the real drift and the virtual drift. And the real drift is, if we really want to be sure about that, we have to have labeled data on essentially what happened after a while. We're showing a customer an ad, and we know if he clicked after some time. We know if he clicked or not. So we have labeled data, again, in some delay. So this is real drift, and we just need to compare that with our data. But there are other ways, even without labeled data, that we could use in order to understand if the model is behaving okay or not. But remember that machine learning, again, is sort of an equation with a bunch of x's and some y's, usually one y, one target. And so if the x values are going to change, there's a very good chance that our result, the result of that equation, is also going to change. And that's something that's very easy to measure. Okay, so we can just look at the information. We can look at a feature. Let's assume there's a total amount balance that we're analyzing on the transaction of the customers in order to determine like the fraud. Okay, and we train on a certain set of data, and the variance of that feature of total income or total something else is a certain value. It has a certain average, certain standard deviation, variance, and so on. And now if we look into the production data, we can in real time go and analyze the statistical behavior of the same feature. So we know what's the average value of the income or the amount of stuff he has in the cart or whatever. We know that in real time. We can calculate it based on a recent time window. And all we need to now do is essentially compare the results of the training, the statistical analysis of the results from our training data for all the features, with the statistical behavior of all the features in the production pipeline in real time. And if we see that those two are not matching each other, then we probably have a problem, and we may want to look into it further. If we do good analysis, we can pinpoint the exact features that changed, okay, and not just look into everything as a whole. And we know that maybe a certain feature now just changed. Total income, again, going back to the COVID example, maybe our total income is now lower because we're not working as hard, or we're not going to work, or maybe the amount of mileage we're driving is now lower, or we're not flying anymore, and so on. Maybe this is only one or two features have changed, and then we need to think about in our model, how do we compensate for that change or accept that change? And there are different ways of essentially calculating that, because again, it's math. We have to come with like an individual value that says, yes, we have drift. And so there are different mathematical ways of doing it, total variation distance, scale divergence, case distance, and so on. Some more details in the blog link that I shared with you. Okay, there's also other unsupervised ways of doing it. We can essentially run clustering on the production data, and this way understand if there are issues or we don't have any issues, if it matches or doesn't matches the clustering in our trader. Okay, so how do we do the detection? Again, there are different ways of doing it. Essentially, you're taking the production data, running all sorts of statistical analysis on that, comparing it with the trained data. So that's one way of doing it. Another way is doing it using time window distribution. So let's assume that there is a behavior that we've learned across a year. And now we run another model that was trained just on the data from the last week. And if those two don't generate the same results, maybe something changed throughout that last week. Okay? So that's another example of how using time windows distribution we can do that. And there are also other contextual approaches, potentially creating additional features that will be indicators, like maybe we put the time as another feature. And then we can see that if that feature of time has an impact on the model behavior. So again, those are different ways that we can use. And how do we remediate? So once we've done this detection and once we have a problem, so there are different ways of trying to fix the problem. Okay, so one is again retraining. If we retrain with exactly the same data and exactly the same code, we're probably going to have exactly the same results. So that's not something we want to do. We want to make sure that we have, for example, fresh data that's more up to date, or maybe again choosing some additional data or joining some additional data that adds more clarity on points that we've identified. So retraining is one way of remediating. Another way is to create an ensemble. Ensemble, the most common ensemble is sort of a voting ensemble. Let's assume we produce different models. We have one model that it was trained on a very long time, on a year worth of data, and another model that was trained on only 1 month, and maybe different models that were again trained on different combinations of data. And we can just run all those ensembles and see which one produces better results over time. So if we see that, for example, the model which has the more recent, was trained on more recent data, is suddenly performing better than the model with the old data, we can give it higher weight. We can start serving more requests from the model that uses more recent data. So essentially, think of sort of a load balancing of the requests, and just shifting more of the requests to the more recent data. There's also like multi-arm bandit approach, which again can address the same problem. Okay. Another thing is that maybe we already have the right model, we're just not using it. So let's think about seasonality. Summer and winter. Obviously, the behavior in summer may be different, especially on tourism and things like that. So we may want to, essentially use a different model that we see that works better for the scenario that we've identified. Okay, so those are the different approaches that we can use to remediate the concept. Okay, see if any special question. Does online learning solve drift to some extent? What about cases where there is a structural break? in the time series. Yes, or would you like to answer? I see you want to answer that. I don't know if you're muted or not.
I think he probably just manages
Okay.
questions. Maybe you can just go ahead and answer it.
I do recognize. Okay, where can I find a copy of the slides and the presentation? So that's probably something to you, Bill. We have I shared a link that has a lot of the content of the slide. It's a blog post that has more details. So I shared it at the beginning. And I assume, Bill, that you guys will share the video?
Yes, yes. Once I have the link, we will share the slides through the follow-up emails.
And regarding standards, I'm not aware of like real standards. I think it's more like unofficial standards for how to do those things, because it's still all relatively new. I don't know of any specific standards. For ensembles, would an XGBoost model need another level of an ensemble? Yes, because again, ensemble doesn't have to be the same type of model. I can actually build two models, one which is TensorFlow, using some time series analysis, RNN or whatever, and another way which is XGBoost, and a third which is using some logarithmic regression. I can build an ensemble on three different algorithms. They don't have to be all the same algorithm. And in some cases, I mentioned that it may actually be different data. Like I may have an ensemble of one model which is trained on the last 1 month data, and another model that was trained on the last 1 year data. Or maybe a model that was trained on a certain group of people, and one which is more general. So I'm trying to hit different models for one which is more generic for the entire population, and one which is more targeted at the specific user that's accessing my site. So that's another example. Good. So with that, I can continue, and we can open it later on to additional questions. Okay. So let's go back into the entire pipeline. So we spoke about this pipeline. It's enormous. It's huge amount of work for any organization. According to statistics of Gartner and other analysts, about 80% of the machine learning projects fail to deliver to production. And that's because that once you have the model in the lab, it doesn't mean that you've built this entire beast that you see here on the slide. You have to have the research pipelines, the deployment, operational pipelines, the governance pipelines, and there are a lot of different challenges, especially when you're using a siloed approach. That your data engineers are preparing the feature, the data scientists are playing around with them, and the MLOps engineer will essentially deliver the actual pipeline and production code, and they're in different departments. That creates a lot of delays and overhead. The other thing that we discussed, if we're going to train the data in research using a data lake with a certain set of features and some computation libraries, and then in production we use different data, different computation libraries, different mechanisms, we likely won't get the same results for production and for research. And also, again, there are other challenges, all this monitoring and so on. It requires a lot of effort. So one of the things that we see in the industry popping more and more, and I understand you guys have a session with Tecton on that, is a feature store. And a feature store is essentially a way to index, catalog, transform all the features in sort of a central framework. Feature store have two different layers inside. One layer is the actual storage or management of the storage. The storage could be traditional databases or data lakes, but you have to index and catalog and provide a lot of metadata on it. And you have to be able to store the same features for online and offline use. Another important thing, not all feature stores have it. Tecton has it, and also the MLRun framework that I'm going to demonstrate have it, is essentially an automated mechanism to build the features and analyze the features and serve and provide the features to the client. So you don't need to go and write SQL queries and all of that every time you need a feature. And you can put everything in a catalog or just pick and choose the features. Now, why is that essential to the discussion of model monitoring and so on? So what we did, what we just talked about a minute ago, that what is drift analysis? It's essentially comparing features in training versus features in production, comparing labels with predictions, comparing the production results with training results, and so on. And how do we compare? Usually we compare using statistical analysis as technologies that we've mentioned. So if the feature store is essentially also the repository for all that statistical information, it makes our model serving, model monitoring, and analysis and explainability and all those things much simpler. And in some cases, even glueless, as I'll show in a demo in a second. Okay, so one of the things that you can look into, there's an open source framework that Guaz is promoting, but also other companies and partners. And it essentially tries to automate this entire pipeline. One of the biggest challenges today, when you have one framework for model serving, one framework for model monitoring, another framework for training, another framework for feature store, and so on, you end up having all the heavy lifting of integrating all those components together. So one of the things that we've created, leveraging different tools in the ecosystem, Kubeflow, Kubernetes, and other tools that are integrated in the framework, is that we created a glue layer that allow you to develop on your sort of client, whether it's Jupyter or PyCharm or whatever, one click deploy something into production on your Kubernetes cluster. You can then store it, whether it's a feature or a function or a service, and then create pipelines, whether it's real-time pipelines or development pipelines for running the training or the production pipelines. And finally, it's all integrated with the monitoring framework. You guys can look into those links that I've shared. Some of the things that I'm going to show are also part of the documentation that's over there. So again, what MLRun has is several layers. One is the online and offline feature store with very flexible data connectivity, so it can work with many different types of data stores, including some of the Iguazio's high-performance data stores. Then it runs on top of a serverless frameworks. There are actually few serverless frameworks, Spark, Dask, Nucleo, Coreboot for deep learning, and so on, about 7 different serverless frameworks that we're orchestrating automatically. So when I need to launch a job for training or run a service for monitoring or serving, it's just like one API call and you get that service up and running. I'll show this in a minute. On top of it, there are specific integrations for the different elements in the stack, the data preparation, the model training, the real-time production pipelines, and the model monitoring, and it's all managed by a single sort of UI and single CLI and API SDK. So that's just a few words on MLRun. And one of the things, it's still not like full production in MLRun. There's already the first versions of that. It's currently in beta. Is the feature store, which is extremely advanced, very, very high performance because it works on top of those elastic engines that we just spoke about before. So you can essentially run any task there on a dozen machines, and it works as seamlessly as you're running it on a single server or container. And the way that it works is that you develop features using different methodologies. I'm going to show that in a demo. Those features are persisted in the feature store. Beyond the persistence of the feature, what happens, every feature is auto-cataloged and auto-analyzed. So all the feature analysis for variants, for histograms, and so on is stored with the features without even requesting that. That happens automatically. You just need to turn on a flag saying, yes, I do want statistical analysis. And then when you're building training, you're just saying, you know what, I need those set of features from a catalog, and you can use them either in offline for training or online for serving. And also the monitoring part is essentially glueless, and we're gonna look into that. One of the things that's very powerful in ML Run is where it uses those serverless engines that know how to do real-time transformations. So you can build pipeline like the one that you see here. This pipeline is developed using a few lines of code. It is documented in the docs repo. So you can build a real-time pipeline that gets data from whether it's a stream or an HTTP endpoint or a batch job, run different transformation like enrichment, pre-processing, ensembles of different models, post-processing, and so on. And you can test it on your notebook, and with a single call, it essentially goes and deploys it into a Kubernetes cluster or even multiple Kubernetes clusters. So this is also used and in those different examples that I'm going to show. And everything that it does is also automatically monitored. So when I launch this thing, it already monitors all the models and all the ensembles and so on. Okay. How does it work? Is essentially you have those nuclear real-time functions, which are again very fast. Think of it like Lambda. It's just about 100 times faster than Lambda, and it supports stream processing and HTTP and many other things. It's also stateful, which allows it to work well with data scenarios. So you have those pipelines that are running on top of the nuclear functions, and then you have those model servers essentially generate a stream of events with all the information from the actual predictions. What data came into the model, which data went out of the model, how long it took, and so on. And this thing is fitting into a stream, and that stream is processed by another serverless function, which is part of the package. You don't need to implement it. And that function is essentially doing all this real-time statistical analysis. So we have the features that are in the feature store and were stored during the training, for example. And those features are grabbed into the serving layer using this API that I'm going to show. And then we have the statistical analysis that compares the actual prediction and the real-time data with the trained data and the statistical behavior of the trained data. And if there are any gaps, it essentially throws an alert, and you can do anything you want with that alert, including running a pipeline using something like Kubeflow or CI tools like GitHub Actions or others. You can build automatically the retraining pipeline, or you can go back and tune the ensemble logic from that event. So that's in general how it works. I'm going to show that in a second. This is one example of how it's monitoring all the data. One of the examples that I'm going to show you is a very comprehensive example. It's actually a real use case that's running in production today. We're using obviously sample data. We don't have real COVID patients here. And this is an example of an application that monitors patient behavior. It monitors the real-time sensors of a patient bed, like heart rate, movement detection, and so on. It has other information, which is like static medical records, the age of the patient, and sort of health situation, and so on. And additional data like measurements. I've taken a blood sample 2 days ago, and I have some results, or maybe some other type of measurements. And in order to build my training, I have to combine all those 3 different types of data into one feature vector. So we're going to see how we're using different tools, different serverless tools to build those features. We can run interactive exploration on those features. And then we're running a complete automated pipeline using MLRun and or Kubeflow together. So we essentially extract the features, we build the training set, we run AutoML on those features, and we deploy a real-time pipeline with an ensemble. And then we have the model servers that essentially use the model and the real-time features from the feature store. Those models generate those serving functions essentially generate telemetry data and statistical data, and which is monitored by the model monitoring framework, and that feeds back into the feature store. So all the production data is stored back in the feature store. So someone that wants to do analysis or explainability research or whatever, he can just use the production data from the same feature store. So this is what I hopefully going to show. Okay. This is, by the way, the blog that I mentioned that Or was the one writing it. So okay, so let's go to that demo that I was mentioning. Again, the first thing that I want to do is bring on all that data that we just mentioned. We have offline data, online data, real-time data, and so on. So the first way I'm going to use is using in MLRun in the feature store. One way of doing it is using Spark. Anyone that likes Spark can just go and create a transformation. You define something called a feature set, and that feature set, has like a key and may have some features. I want to learn the features automatically because I'm sort of a bit lazy. I don't want to go and fill the features one by one. And so what we'll do is we'll create a feature set. We'll give it a source. A source is a Parquet file. Again, there could be many different types of sources. And then I'm just going to ingest, to do ingestion into the feature store using Spark, just giving it like a Spark session context. And as I mentioned before, I want to infer all the options, statistics, histograms, schema types, and all that. That's essentially what it means. And so now, if I have all the statistical analysis of those features, I can use that automatically for the drift analysis. So that's one way of doing it. And again, I have all the results and all that. Another simpler way of doing it is using just Python. Again, just taking your data frame, Python data frame, running feature store.ingest, and again, you have that feature set in the feature store catalog. This is an example of this measurement set of features. Those are the features. And you see it automatically gathers all the statistical analysis for every feature that I ingested. Okay, but now let's assume we have something a bit more complicated of building all sorts of transformations on our features. So in this case, I want to take the patient's data, and because it has like the age, I want to change the age to an age group. I want to build like one-hot encoding for that age group, and potentially any other thing like imputing missing data and so on. So now I want to build a pipeline of a bunch of transformations. So it takes the source data, which could be batch or an operational database, do all those transformations, and it will automatically store the data in two forms, in NoSQL and in Parquet. You can define what kind of stores you want to store the data on. And also, it's very important in the development phase to see what's going on. So we can just go and infer our pipeline. Essentially, we simulate our entire pipeline inside a notebook because we want to see that it's producing the right features before we actually write it into the feature store. So we're just going to push some sample data. We see that our one-hot encoding was made properly and all that. And then we can just go and do ingest. And now let's assume we want to do this ingestion in a schedule every hour. This time we don't ingest, we just say, I want to run an ingestion job, which is like periodic, for example. I can give it a cron string and other things. And I give it the source, so it defines the job information, and then just run this thing. It's using the serverless engines in MLRun, which will essentially go and launch a set of a job, whether it's periodically or real time on the Kubernetes cluster. It could also be a scale out job that actually is spread across multiple containers. And you see it's essentially doing this analysis. And now the last, the problematic feature is the real time, is the bed sensor data that keeps on coming all the time. And we need to do things like aggregates and all of that. So here we're also putting some data validation rules and creating that sensor data, creating some custom processing classes that will be pushed automatically to our serverless functions. building some aggregations across the different sensors. So again, with few lines of Python code, I built a very complex real-time pipeline that does the processing of those features. And then I can just simulate it on my notebook and finally just deploy it using, in MLOps, there's something code to function, which essentially translates your code to a microservice, and then just deploy that service into production. That's it. Now I have all those features are ingesting into the feature store, and all those features are covered by statistical analysis. So I don't need any manual work to do all the drift later on. By the way, I may want to also push label data, whether it's in a delay or for training, and I would probably put the label data as another feature, separate feature set that will be joined based on the timestamp or the shifted timestamp of the event. So in order to do the drift analysis, we would need the label data to do a join with the label data and measure the accuracy. So this, what I did right now was essentially covering all the ingestion part. Now let's do training for our data. So remember, I have a bunch of different data sets, the sensor data, real-time sensor data, measurement data, and so on. So what I'm doing, I'm just creating a feature vector off of all of those individual features. And then I'm just saving that feature vector. Now let's assume I want to use that feature vector. I just say, give me that feature vector. I want to look into that, so I can just print it out. So this what you see here is the full analysis of my features. Those are the 52 features that are joined from 4 different data sets, including the labels. We're using time traveling to combine the features, so they'll be correctly joined based on the timestamp of the events. And in order to train that, we go to MLRun to the pre-baked functions. The marketplace or the hub has AutoML functions. So you can essentially say, give me a scikit-learn AutoML classifier, give it some mount point, and just run it with 3 different algorithms. And that thing will generate 3 different models, random forest, logarithmic regression, and other boosts. I could even put other things here. I may want to train with TensorFlow or some other mechanism, but that automatically creates all those different models. So if I'll go into my project screen to the model tab, I will actually see the different models, and I could look into the, all the information and accuracy and deep dive into those specific models. So with that, I've also already completed most of the work. I did the training, I did the data engineering, and now let's do some serving. Okay. So in the serving, you have pre-baked functions in MLRun for serving, but this case I want to show how it works. So I can build a serving function. It behaves like if some of you work with Triton or KF serving, it behaves the same, just much faster, and it's serverless. So I build a serving class which has like a load. This is where I'm loading my feature service, and then I'm pre-processing, which is where I'm enriching my real-time features with the feature store features, and then I'm just doing a prediction. So this is a class for doing model serving. In order to build an ensemble, again, I take my code, make it a microservice. I define some topology, different types of topologies. Some are very advanced, and just say, what, add those 3 models that I have from the model store, just add them to this function. Now let's assume I want to test my function locally in the notebook. I can just go and give it the training set, the offline features, and run it in a loop and see that my model is behaving well. I can just run some tests and see that it's producing the right results. And you see, because I did inference from the root of the models, essentially it's the voting ensemble result. I can also go and ask for a specific model. If I do like /m1/infer, it will go to the specific model. Now here comes the part for the only thing you need to do in order to do model drift detection and model monitoring is just set a single parameter, say set tracking, which turns on the tracking for that microservice function, and deploy, which means deploy that function. and then that function becomes a real endpoint. So if you go into the Nucleo screen, you'll see that you have functions. They have configuration, which could also be defined through the API. Auto scaling, GPUs, and so on. You can have a variety of triggers. If you want to use streaming technologies like Kafka to do your inferencing or anything else, again, it's one click away. If you want to add like canaries and things like that to your function, again, it's one click away. And all that is part of the open source Nucleo and MLRun frameworks, by the way. So again, I deployed the model, and now I have a running model in production. Now, all of this model, as I mentioned before, it's writing back into the feature store and also being monitored by the model monitoring piece. One way of looking at it, let me refresh the screen. So this is an example of the Grafana dashboard. For that, so I can actually see, I still don't have the, because it was just loaded, I still don't have the drift and accuracy analysis. Will come later, but essentially I can see the 4 individual models and their behavior, which is being analyzed automatically. Okay, so we closed the entire loop. We did data ingestion. We did the training. The training, by the way, can also be done using Kubeflow. So the same, this is using Kubeflow. It's part of our managed platform, but it's also open source. So you can build a more advanced pipeline for the training that triggers every time that the drift changes or you want to retrain, you could essentially trigger the full pipeline. You could also do that through Git integration, sort of a CI/CD fashion. So with that, you have essentially the entire loop that we've discussed. So we talked about bringing the data, doing interactive exploration, running the complete training, building the models, working against a real-time feature store, monitoring the models, and finally, we can also do other analysis on the same data. This is, by the way, how it looks when the actual results are already calculated. So, and you can actually zoom into a model and see the individual features, and every feature, the individual statistical analysis over time for every feature in your model. And because there is sort of a stream processing engine that takes all the data that you've ingested from the model and analyzes that in real time. Okay, so with that, I finished the demo part, and maybe there's like Q&A or okay. Any questions or?
Great. So I see we have quite a few questions in the Q&A. I'm not sure I will cover that yet. Just to make a reminder to everyone, if you have questions, please feel free to post in the Q&A. And again, if you prefer speak to ask questions, you can raise your hand. We can unmute you to speak to ask questions or even discuss comments on questions too.
Yeah, so there are a few questions here. I'll try, it's not necessarily chronological, but I'll clear them. So there was a question, can we use MLRun? Yes, you can. There's also a nice Katacoda tutorial how to install it open source under Kubernetes. In Iguazu's situation, Iguazu is more of a managed platform. There are many other features on top of it, like security, authentication, data processing layers, managed services, and so on that you get in addition. So usually people play around with things like MLRun, or they have their internal DevOps using it, but when they get to scale and performance, they're looking for something that just worked and supported. So that's on that. Okay, please highlight the difference between MLRun and MLflow. So MLflow is mostly a tracking system. So it tracks your code. You do like log you log your results, you log your artifacts, and so on. And it has maybe some other automation tools, but MLRun is like a full orchestrator. You've seen it. It has serverless engines. It has a feature store. It has serving pipelines with real-time pipelines. It has integration with Kubeflow, essentially a layer on top of Kubeflow for automating different pipelines. It has it scales out everything that you're running. If you want to run a deep learning job, it knows how to orchestrate the job as a sort of a scale-out system. So it's more oriented towards the operational challenges. It also has an API and SDK for doing log tracking and artifact tracking and all that, like MLflow. The main difference is that in MLRun, it works all the time. It works in the research, in the production, whether it's in a Kubernetes job or on your laptop or PyCharm or notebook. So you do the instrumentation once, but then it's applied to any place that you're going to use exactly the same code, which is not the case in MLflow. How often can you use supervised drift detection? How do you have a decent fast feedback loop? I'm also curious to know what extent you think that we can capture model deterioration by detecting virtual drift. Okay, so there's a lot of questions in one question. So first, we turn it all the time for customers. We turn it all the time. So maybe it also depends on the type of application that you have. If you're doing predictions in a very static manner, then you don't need to make decision every few minutes. But if you have like applications that are more real time, like we have applications like you see patient deterioration analysis, obviously you want it to be very accurate. Or if you have something like fraud prevention logic, there's a lot of monetary impact if your model doesn't behave. But on the other hand, let's assume you're doing predictive maintenance on a machine that you get statistics once every hour or every 6 hours. Probably it's not as critical because machines probably won't misbehave in a matter of seconds. That's in general. And you can also approach me offline if you have additional questions, or everyone can approach me through LinkedIn. I'll be happy to help. What site app is used for projects? And another tab in the presentation. So that's all part of MLRun. That's the beauty of it. Again, this is those projects. I can just go into a project, and in the individual project, I would see my scheduled jobs, my feature store, my models for that project, for the real-time function used in my project, how many resources are used by my project, those API gateways that I mentioned. Everything is covered in one place, which is really the great thing about it, that you don't need an army of DevOps people to make sure it all works. That's answer. And about pushing labeled data. So again, it's using exactly the same functionality that we use for ingesting any other feature. Labeled data is just yet another feature. And because of the time travel join capabilities of the feature store, you can just combine labeled data with other feature sets as well.